We're going to start here in chapter 9 with Amdahl's law. This is a professor of math or something, still actually alive. This is not, it's kind of an equation. I would call it Amdahl's equation. Basically what we're interested in asking is, if we speed up part of a process, what is the effect of that speed up on the whole process? So for example, I could give something nothing to do with computers. For example, if I'm making pancakes and I, have to mix the batter and break the eggs and put the milk and all the things in and mix the batter, that takes a certain amount of time. And then there's the frying of the pancakes. If I all of a sudden take out 2 frying pans, I can speed up the part of the process that's involved with making the actual pan, with frying them, because I now have 2 frying pans. I can fry them twice as fast. I can make them faster. But the first part of the process of actually mixing the ingredients is fixed. I'm not going to go any faster just because I have 2 frying pans now. So the question is, how much does that help us? How much does the part of the process being improved affect the whole overall speed up? Questions so far? Okay. So here's an equation. S is the latency. That means the theoretical speed up of execution of the whole task. So S is like the speed up that I'm going to get. Of course, we're talking about like a percent here. So that's why it's 1 over something. How much faster is it than it was before compared to what it was before? In other words, if the process took, let's say 10 minutes, and now it takes 5 minutes, you could say it's 5 amount faster, it's 5 minutes faster, but it's twice as fast. Why is it twice as fast? Because I did it in half the time. It's kind of a funny, if you can talk about fastness and you can talk about time. If you talk about time, it's half as much time to do it. It's now only 5 minutes, not 10 minutes. But it's twice as fast. Well, how can you think about that? Because I can do the process twice in 10 minutes. It used to take me, I could only do it once in 10 minutes. Now, how many times can I do the process in 10 minutes? 2 times. So it's twice as fast. So it's 1 over the quantity, 1 minus P. Now, what is P? P is also called the fraction. It's the proportion of execution time that the part benefiting from the improved resource originally occupied. In other words, if it normally took me 5 minutes to mix the batter and 15 minutes to fry the pancakes, so the fraction of the part of the process, there's the fraction of the process that I was able to speed up would be 15 out of the total 20 minutes. So that would be 75% of the process. That's what P is. P is that 75%. So if you think about this, this is 1 minus P. So that means the part of that 1 minus P will be the 25%. That would be the mixing of the pancakes. That would be the part of the process that I can't speed up. So that remains. That's 1 minus P. So 1 minus the 75%. Plus P over S. So S, this is little s. The S on the left is big S. This is little s. Which means it's the speed up of that part of the process that I can speed up. In other words, how much did I speed up the making of the pancakes? That's the S. And the P is that proportion. P is really for proportion. Is the proportion that got speeded up. So 75, that would be, P would be 0.75 divided by S, which would be the speed up of that. Well, what is the speed up of that? So we have to think, let's take another example. In other words, what is the speed up of that? Well, if I get 3 frying pans, now instead of 15 minutes, it's going to take 5 minutes. So the speed up will be 3 times faster. right?
And wait, so what's the big S? What's that again?
That's the total. It's written right there. The theoretical speed up of the execution of the whole task. Of the whole task. Keyword there is whole task. In other words, if I would emphasize something, it would be this, of the whole task. And this is the speed up of that part of the task that benefits from the improvement, right? Good?
Yes, thank you.
Okay, so let's do, for example, if a program needs 20 hours, so now we're talking about a real program, not pancakes. Let's say, because this is of course relevant to programming, or to it's actually hardware. We're talking about speeding up the hardware. If a program needs, let's say for a given program, it takes 20 hours using a single processor core. And a particular part of the program, which takes 1 hour to execute, cannot be parallelized. And that's like the mixing of the batter. It cannot be improved. If we can parallel, when I put 3 frying pans, by the way, my example is an excellent example because it's the real world example and it's exactly the same idea. Because by putting multiple frying pans, you are parallelizing the task. You're doing in parallel the activity. So while the remaining 19 hours, that would be 19%, P equals 19%, that's the proportion that I can improve, can be parallelized. Then, and now we're talking about a theoretical thing here. Now we're going to say, let's say I parallelize this. I got the frying pans. I have an infinite amount of frying pans. Of course, with frying pans, it still takes a certain amount of time to, here's where the example fails because, it still takes a certain amount of time to fry even one pancake. But imagine a certain computer process. If I threw at it an infinite amount of CPUs, it theoretically would be finished in an infinitely small amount of time, which we can call 0. So there still will be a bottleneck, however. There still will be something holding me back. That 1 hour that I cannot parallelize. Not paralyze, parallelize. That I cannot do in parallel. So that's what we write here. Then, regardless of how many processors are devoted to a parallelized execution of this program, in other words, I'm going to throw at it how many as I want. The minimum execution time cannot be less than that critical 1 hour. In other words, the 1 hour, which cannot be parallelized, is going to hold me back. It'll be 1 hour plus something, plus a tiny amount, which we can call 1 hour. So the theoretical speed up is limited to at most 20 times, we can say. In other words, if 19 hours can be parallelized, then at best I could do it 20 times faster. Why 20 times faster? Because in a given 20-hour period, now I can do the task 20 times, as opposed to only once before. Is that clear? Questions? Okay, so let's throw these numbers into our equation and see if we get the 20. Just to check if our equation is right. Here's our equation. So we say 1 minus P. Now, why do I write 1 minus P? Look at this note here. Note, because the S is the speed up of the part that can be speeded up. Well, let's assume that's infinite. So then P, which is the part that can be, which is the 19 parts, divided by infinity is 0. When you divide something by infinity, you get 0. I mean, you can't really divide by infinity, but because, as we're saying,
that as x gets closer to infinity, P over x gets closer to 0.
Exactly. If I divide something by something very large, that fraction becomes very, very small. 1 over 100 is very small. 1 over 1,000,000 is even smaller. 1 over infinity is 0, so to speak. Let's view it as 0. So that means that this part of the equation drops out, and then we just have 1 over 1 minus P. So 1 over 1 minus P equals 1 over, well, what's 1 minus P? P, we said, is 19 out of 20. Well, if we put that into percents, that's, we multiply it by 5. So then, right, the 20 becomes 100, so it becomes percents. And now we get 1 minus 95%, which means 0.5%, and it's 5%. So 1 over 0.05. And that happens to equal 20. Because you're dividing something by a fraction. So it's like multiplying. So we get 20. And that's what we should have gotten. That's the speed up. That's the theoretical speed up where I have an infinite number of processors. Obviously, if I had, the speed up was only 2 here, then this number, then I would be dividing by a lot, not such a small number, but by a larger number. So this number would be smaller, right? As this speed up, if this speed up would be 1, imagine it'd be 1, then I'd be adding 95, it'd be 1 over 1. The speed up would be 1. In other words, if the speed up that I was able to do was nothing, was just 1, that's not speeding up at all. Then this would turn into 1. Then this would turn over. Then the whole thing would be, 95 and 5. It would be 100. So it'd be 100. It would be 1 over 1. What did I want to say now? So, well, it's to me, it's sort of funny because this equation is not such a big deal, in my opinion. I have a question. It's just sort of obvious, but he got to be named for eternity by coming up with that equation. Yeah, go ahead.
When you say, like, we got our answer to be 20, what is 20? Like, is it a unit of speed? What is it?
Oh, you might call it a unit of latency. I don't know. It's our S. It's our latency.
But what's latency measured in?
Just a number. No units.
Okay.
Because it's the speed up. It's like saying how much faster the car was running at 10 miles an hour and this car's running 20 miles an hour. How much faster is it? The miles per hour go out of the equation when you divide, and you just get 2. It's 2 times faster.
Is like the amount of times that it is faster.
How many? Yeah. In Hebrew, like P comma, you would say in Hebrew, P comma yoter maher.
Meaning, if S was 1,
how much faster is it? What?
Like if S was 1, that would mean it's the same speed.
Yes, exactly. If S was 1, I didn't get any speed up at all.
Okay.
If S is 2, then I doubled my speed up. If S is 1.5, then it's, I don't know, 1.5 times faster. Now, in the book, Weinman, he sort of came to this equation in 2 steps. And I'll show you. I'm just going to explain it again now, in a slightly different way. If we have a program that the execution time for it on a certain processor is execution time old, okay. If we improve the processor, here we talked about improving the processor, but you could imagine it also adding another processor. Either way, it's getting processed faster. If we improve the processor such that a fraction of the runtime of the program will run speed up times faster, well, that's kind of what we just said. What will be the runtime of the program after the improvement? So now we're actually doing something in numbers, like you asked about units. Now we're talking about in seconds. What will be the runtime? When we talk about runtime, we're talking about seconds or nanoseconds. So we can say an equation like this, and he just throws this out here. And you see, it's, by the way, it's the same thing we had before. 1 minus the fraction, that's our P, plus the P over the speed up. That's the same, that was our denominator before. Now it's going to be not our denominator, it's just sitting here. Because it's a slightly different equation, because we're multiplying it. In other words, we're going to take, now this is the speed up, but now we're going to multiply it by the old time, and that's how much faster the new time will be. This, in other words, if it's this number times this, will give me the new execution time. So he says like this, execution time old times 1 minus a fraction is the time for that part of the program, which can't be improved. Let's call this X. In other words, the old time minus the fraction is the part that I can improve. In my example before, it would have been 95%. So 1 minus 95% would be 5%. 5% times the old X times old execution. 1 minus the fraction is the part of the program that can't be improved. Well, that makes sense. It's not only the part, it's the time part. It's the part in time.
Wasn't the original latency equation 1 over that number that's highlighted right now?
Yeah. This is not the latency equation. We're going to get to the latency equation. This is just a preliminary step. That's why I say divided.
Can you go back to the previous equation a second?
Yeah. You see that this thing over here, 1 minus P plus P over S, that's what he's got over there. That's this. 1 minus P plus P over S. But you'll see that it's going to turn into that. So first of all, he's trying to explain what this is. But notice that this is not speed up. This is not the reason why it's not exactly the same equation is because we're not expressing the same concept now. Now we're expressing a concept of time. Before we were just talking about the relative improvement. Now we're talking about an actual time. So it's not the same exact equation, but it's got that same part. And now he's explaining that he's trying to appeal to your common sense and say, well, wait a second. 1 minus this fraction, that's the part that I can't times the, that's I'm stuck with. That part of the program, that's the 5 minutes of mixing the batter that I can't improve. What about the 15 minutes of, multiply the old times the 15 minutes, in other words, the portion, the 3/4 divided by the speed up. It's 3 times faster. So it'll be 3/4 divided by 3 will be 1/4. So it'll be 5 minutes plus 1/4 of the old execution time. The old execution time was 20 minutes, let's say. So it'll be 1/4 of that, 5. So now I'll get 5 plus 5, 10. So that's the new execution time, 10 minutes. Because that makes sense, because the 5 minutes for mixing the batters remains. The 15 minutes is now divided among 3 frying pans. So it's 3/4 divided by the speed up. Well, the speed up is 3. I got 3 instead of 1 frying pans. So 3/4 divided by 3 is 1/4. 1/4 times the old execution time. The old execution time, the total old execution time is 20 minutes. So 1/4 of that will be 5 minutes. So 5 and 5 is 10. So this equation makes a lot of sense.
So the speed up would be 3. Like let's say if we added a CPU, so the speed up would be 2 instead of 1.
Yes.
So it's not like a percentage like we were doing before. It's the amount. It's like the latency.
No, the
the
fraction is the percentage. This is a percentage. What I call fraction here is what I called what I called P in the previous one.
So what's the speed up here compared to the previous one?
No, we're not calculating the speed up. You can't ask that question. Oh, the speed up over here?
Yeah.
I just told you. In my example, it would have been, in my example with the pancakes, it's 3. If you only have 2 frying pans, then it would be 2.
So speed up is kind of like the latency for only the part that's affected?
Yes. It's the same as the S that we had over here. This S is the speed, is that S, is the speed up of that part of the task that benefits from the improved system. Well, I now have a frying pan system, and that part benefits. And that part benefits by how much? Well, I have 3 instead of 1. That's 3 times.
But what's the speed up in this example right here on this page?
There's no numbers here.
No, go back. There, on the example at the bottom, what's the speed up in that example?
Infinity.
Okay.
Infinity. That was what we said. This is a funny example. The example
because
is
we added
we added an infinite amount of CPUs. That's why
okay.
It broke down, because by pancakes, even if you have an infinite number of frying pans, you'll still take some time to make pancakes. But in a computer, it's a little bit different because, you'll take one clock cycle to get everything done.
Yeah, we could say it's like builders building a wall.
But again, it takes, even to put one brick, in other words, there's a certain, if it takes, 100 men, if it takes 100 men an hour to dig a hole, how long will it take? How long will it take 1,000 men to dig a hole? That math is not right, because when you have 1,000 men there, they're pushing at each other and they're getting in each other's way. And if you have an infinite,
though, it could be long.
And if you have an infinite number of men, well, it won't take zero time. If we take an infinite number of men, you'll save a lot of money because you'll pay them nothing because they worked a zero amount of time.
For computers too, you can't have less than one command, meaning the minimum you could do is even if you have a CPU per command. So the command is like one brick.
Right, the minimum, exactly. So exactly here, so my frying pan example is the same. One pancake fry. Just taking an example, how long will it take to make 1,000,000 pancakes? Anyway, the point is, this is theoretical because there is no number infinity. As my 4-year-old said, infinity is not a number. When asked by his 12-year-old brother, count to infinity, he said, I can't. Infinity is not a number. I think he just thought he was being tricked. But anyway, explanation. Okay, so we explained that. Now, what about the other part? So I really just explained this whole thing, but this part we explained is the part that cannot be improved. So that's the fraction, in other words, that remain, though 5 minutes for the mixing. The x time, but now this is just, we have a distributive law of mathematics, which means we distribute this number to both parts here. So we'll distribute to this part. So old time times fraction divided by speed up is the runtime for the part of the program that can be improved. In other words, 3/4 of the program can be improved. By how much? By 3 times. So that's 1/4 times the old execution time, which was 20 minutes. That's 5 minutes. So that makes sense. This is the runtime of the portion of the program that was improved. Let's call this Y. So it is then clear that execution time equals X plus Y. Duh. I mean, that's, he's just trying to appeal to your common sense that this equation makes sense. Okay, and he calls it X and Y. Now he goes to our equation. And he says, well, what is speed up? And this is very important, by the way, in lots of subjects, because, if you're talking about money, let's say, how much did my money improve? How do you calculate my, if I had $1,000 yesterday and today I have $1,002, how much, what rate of improvement did I get? What rate of growth in my money did I get? So I got, I don't know what the equation is, but whatever. You basically have to divide one by the other, and you have to do it in the right way. So here, what we're going to say is speed up is the old time divided by the new time. And that makes sense also. Why? Because the old time is 20 minutes. How many times can I do the new thing in that? So I divide the old time by the new time. That's how much faster. In that same 20 minutes, I can do the 10 minutes twice. The 10 minutes of the new execution time goes in there 2 times. 20 divided by 10 is 2. So the speed up is 2. So this is like, for a mathematician, this is explaining what he means by speed up. You're asking, what is speed up? Well, speed up is by this equation. The old time divided by the new time. How many times the new time can go into the old time? And I get 2. Now, if we go back here and we say, well, let's use, if execution, here we have execution time, new is equal to the old one times this. So this means that let's assume, basically like this. If we go back here, we don't know. We want to make this theoretical. So we'll say for any execution time old, we'll call that 1. We'll say if it took 1 hour, then what will be the new execution time? So to make this equation simpler, we're just, it's a theoretical equation, we're going to assume that execution time old is 1. So if this is 1, that means execution time new equals this. And what does execution time old equal? Well, we just said 1. So if we're going to do old is 1, then new is that whole thing over there with the 1 in front, with the 1 we can remove. So that is exactly the equation that we saw in the first slide. Latency equals 1 over 1. So basically, I just derived through a little bit of common sense and math. I just derived that equation. Okay, is that clear? Questions? Good. Okay. So now that we have mathematically proven that, I mean, to me, I hesitate to call this math because, you know, it's just common sense, but it's a little bit of math. Sample problem. Okay, so here we're going to try to use our equation to actually solve a, you know, I don't know, test question. Anyway, we have a modified process as follows. The floating point instructions. All right. Floating point instructions will run to, so now we're going to talk, this example, we're not going to talk about having a new processor, but we're going to talk about certain types of instructions. Let's say we have a new processor. Remember, we're talking about like computer performance. So let's say we have a new processor and we're comparing to an old processor. And the new processor, he does his floating point operations 2.5 times faster than the other guy, which again means in a given amount of time, he can do 2.5 times more instructions. And the memory access operations are 3 times faster. Every time he wants to do a load word or a store word. Integer addition and subtraction are 1.5 times slower. Oh. And there's going to be a lot of those addition and subtractions, and they're slower. Okay. Running a benchmark program. Now, in other words, we're going to have to see, well, what's the distribution of these commands in a given program? If a certain program has no floating point instructions and no memory access, it's just addition, then our new computer is going to be obviously 1.5 times slower. But so it's the program we check it with, we're going to have to figure out what's the distribution of all the various commands. You see that this example is a little more complicated because we're not just talking about one part gets speeded up, the other part remains the same. We're talking about several parts. So running a benchmark program reveals that floating point operations consume 15% of processor time. Okay, remember our pancake example? So 15% of the time we're doing, you know, mixing. That's our floating point operations. And we can speed that up a little bit by 2.5 times. Memory operations take 20% of the time. And integer and addition and subtraction takes 40% of the time. How much is that together? 20 and 15 and 40? Is that 100%?
75.
75%. Why is it not 100%?
Because the other part can't be improved, obviously.
Right. So there are other instructions that are not there, that are not floating, not memory, and not in addition. They're branches, for example, or jumps. And those ones are not improved or deproved, I don't know, or made worse. So how much did we improve the processor according to this benchmark program? That's a very important addition there. According to, we cannot give an answer to the improvement in general. We can only say for a particular program, which is why, you know, you can say this computer plays games faster, but watching videos, it's slower, you know, it could be. Not everything gets improved necessarily. Okay, in other words, find the speed up overall. What is our improvement, again, for this particular program? So let's go to the next slide. So basically what we're going to do is going to take, what is this? This is the 15, the 20, and the 40. Together, that becomes 75. 75% is what we change. In this case, it's not improved necessarily, it's changed. And the 1 minus that is the part of the program that we didn't improve. And he's going back to this. The way Weinman did it is he went back to the original execution time. And then he's going to divide them and get this. He could have just jumped. I don't understand why he didn't just jump straight to this equation. He's starting with this one and then, whatever. He could have just jumped to this equation, but he did it a slow way. Maybe that's good. So 75%, 1 minus 75% gives me 25. That's the part that I can't improve. Plus the part that I can improve. Well, what is that? Well, the 15% of I can improve by how much? By 1 over, it's 1 over the improvement, S, because remember, it's fraction, which is 15%, times 1 over speed up. In other words, when you write fraction over speed up, you could also write it as fraction times 1 over speed up. That mathematically is the same thing, which I hope you know. So 1 over the speed up times the 15. That's how that part got speeded up. Then the 20% got speeded up by 1 over 3. Why 1 over 3? Because it says over here. Oh, now I see this also. 1 over 3 because 3 times faster. The memory axis, that's 20%. 20%, 1 over 3. 20%, 1 over 3. But the 40% of the addition subtractions, it's not going to be 1 over 1.5 because that would mean it got 1.5 faster. If it got 1.5 slower, it's going to be it's going to be reversed, 1.5 over 1. We upside down. Of course, we don't have to write over 1 because that's obvious that you could just remove that 1 on the bottom. So it becomes, instead of 1 over 1.5, it becomes just 1.5. So if we just add up all this stuff, so we say 1 minus this, etc., plus, he just now writes them a little bit. I just copied this from him. He just now writes them 1 over the other, 1 over the other. He just does it the long way, and now he didn't really get anywhere. And then he just plugs it all into his computer, into his keyboard, into his handheld computer, and he gets the old execution. The new execution time is the old execution time times 0.98. So did we? First of all, right away we should see is the new computer better?
Yes, by 2%.
Exactly. Well, you could say by 2%. That's exactly the question. It's 2% better, but what we say is actually it's 1.02% times better. In other words, it's a question of how you. Again, it's a question of phraseology. You're right. You could look here and say, it's 2% better. But what the answer we want is old time, which is 1. Because why is it 1? Because we're assuming we don't know what it is, but we're assuming whatever it is, it's 1. The relative relationship is 1 time, divided by 9.8. So 1 over 9.8 is 1.02 times faster. Call that 2% faster, but you have to multiply. It's confusing. You have to multiply you see, that's the thing. If you multiply the old times, well, what do you get if you multiply 0.98 times 1.02? Do you get 1? I don't think so. Shouldn't get 1. In other words, the new time. See what I mean? It's confusing a little bit. But that's what you got to do. Old time over new time. How many times could I, in the same time that the old time did, how many times can I do it now? I can do it a little bit more. I can do it not just 1 and 1. I can do 1 and a little bit more in that same 1 amount of time. Okay, so that's the speed up overall.
I just checked. It's like almost 1. It's like it's 2,499 over 2,500.
What? No, I just asked what is 1.1 times 98.
Right. No, but you also asked whether 1.02 times 0.98 is 1.
Right. And you told me it's what?
It's almost. It's 2,499 over 2,500.
Ah.
So like there's some digits after.
Gotcha. Okay, so it's almost. That's a little bit weird. It's a little bit of a different question, you see. That's what I'm saying. The speed up is 1.02 times faster, whatever that means. But it means what I said. It means that it's a funny number because it's such a small amount. If it would be 2 times faster, we could understand. You can do it if it's 2 times faster, then that means in the time of, like in my example of the pancakes, I can do it in 10 minutes instead of 20 minutes. So it's 2 times faster. Okay, that's it. That is Amdahl's law. I think probably in the homework you have another example, which you can do yourself. It's pretty, I mean, it's a little bit confusing, but the math is straightforward. Let's go to chapter 10.